Okay, here I am. First of all, I want to thank Mike for the invitation to this conference, which looks like it's going to be very exciting. I'm really looking forward to it. I'm always happy to come to Cambridge, so it's nice to be back. I also want to say thanks to all of the Newton Institute staff who make it so smooth to come and visit here and everything. So I really appreciate that. Okay, so I'm going to talk about some work that we've been doing just over the last couple of years. It's a collaboration with Matt Helgeson's group at UC Santa Barbara. And so here's Matt here, and I'll talk at some length about some really fantastic experiments that his group have done, particularly Patrick Corona, who graduated from the department a few years ago, and Inuk Dutta. And most of the work that we've done on this has been done by two fantastic former postdocs of mine, Charlie Young and Manish Kumar. So the motivation for this, coming back to Mike's comments about industrial problems, so real industrial processing problems involving complex soft materials, they're never viscometric. There's some complicated flow profile involved in the process. While our experiments in generally are viscometric, it's a simple shear flow or maybe a uniaxial elongational flow, but not the kind of things that you often see or typically see in applications. So here, just as one potential application, this is work from Yingao's group at Illinois. She's interested in making flexible electronics using conducting polymers, and the process she has gone to a lot of work to engineer this coating process to make sure that the polymer molecules are aligned and oriented. And so that's the kind of application you can have in mind where you really want to engineer the microstructure of this soft complex material. Despite the best efforts of many people, we lack accurate first principles model relating flow, microstructure, and stress in realistic complex fluids. And then again, this is sort of an issue that was addressed to some extent in the experiments from Matt Helgeson, which I'll describe. We don't often have spatially resolved microstructure measurements in the same kinds of situations where you have industrially relevant flows. Okay. All right. So the question that I'll try to start answering here is, can we use big data from new experiments along with math and computing, some machine learning and optimization to circumvent some of these limitations? So that's going to be the overall topic of my talk. So the first thing I want to do is talk about this really great experiment that Matt's group has developed. So many of us will know about the four-roll mill, which was developed by G.I. Taylor somewhere right over there, I believe, about 75 years ago. And the idea of the four-roll mill is to generate a well-characterized linear flow at a stagnation point. And so that's what Matt's group has done in a setting in materials where you can do X-ray scattering. So Susan Muller actually was the first to develop a fluidic, microfluidic, actually millifluidic version of a four-roll mill. And the idea is that you engineer the device geometry and the inlet and outlet flow, so you get a linear flow of the desired type right at the stagnation point in the middle. All right, and Matt designed this so that you could do velocimetry in the flow, so particle tracking velocimetry. And you could also put this device in an X-ray scattering apparatus and do scanning X-ray scattering. So here are streamlines from the device. Here is just a float type parameter, so extensional, shear, rotation dominated flow. And then the bottom set of pictures here, the color is just indicating an average orientation angle from the scattering pattern. Okay. And what's really nice about this now is that having the flow data and having the scattering data, in principle, you can move along a streamline here and basically interrogate the Lagrangian history of the microstructure in this flow, right? And let me say from the start, this was originally designed, as a four-roll mill to do linear flows. What we're actually interested in is the regions away from the center, the stagnation point, where the flow is not a linear flow anymore. And you'll actually see that the velocity gradient is changing as you move along a Lagrangian trajectory. And that's the key feature of a real processing flow that we want to capture. And actually future work, there'll be a bullet on my last slide, talking about how we want to move away from this four-roll mill geometry, because that's not obviously the best geometry to look at if you're interested in coding processes, for example. But this was the initial geometry where we got things, where Matt's group and our group got things going. So that's what we're working with so far. Okay. Just a little bit more about that system. So here again, we've got you can see, so there's particle tracking bell symmetry. So you actually are directly finding Lagrangian trajectories through the flow. And here what they've done is just mark out 4 spots along this trajectory. And here's a scattering pattern at each of those 4 spots. The fluid that we've been working with, it's a very simple complex fluid. It's just a solution, actually a dilute solution of rigid rods, so cellulose nanocrystals, the initial experimental system, where the scattering patterns are quite simple. You're essentially just seeing the degree of orientation in those scattering patterns. And so we've got data for microstructure along these Lagrangian trajectories. In principle, you can do this for lots of different Lagrangian trajectories. So you have a lot of data to work with to connect the flow to the microstructure. And that's what we're aiming to do. And so this is this kind of thing you put in a proposal for this work. So Matt actually came up with this name, Scattering Informed Microstructure Prediction During Lagrangian Evolution, or SIMPLE. And the ultimate idea is to be able to take experiments like I just described, take some modeling tools and use those to learn evolution equations for microstructure and flow from these experiments, and ultimately to make this final step to actually do model-driven design for complex processes involving soft materials. So that's kind of the manifesto for what we'll be doing. All right. So the framework we've developed is the following. So we want to learn governing equations for microstructure. I'll talk a little bit about stress later, but initially, so the scattering patterns only directly give you information about microstructure. There's another step if you want stress. All right. So we want to learn evolution equations for the microstructure in terms of the velocity gradient, so the usual thing, using form SAC, so that's fluidic four-roll mill scanning small angle X-ray scattering data, form SACs. Okay. So each of those scattering patterns is a large number of degrees of freedom, might be 100 by 100 pixels. We don't think that you should need 10,000 pieces of information to model the microstructure, especially in this simple fluid like this. So there's a first step, that's a dimension reduction step to find a set of descriptors that, a small set of descriptors that will be sufficient to characterize the scattering patterns. I'll describe all these steps in some detail. We want to build in the key symmetries of the system. That first of all, there's just a rotation symmetry, and again, I'll talk about this in more details. If you rotate the experiment, you rotate the scattering pattern. There's just simple rotation symmetry, but there's an important dynamical symmetry, which is material frame indifference, which is that the microstructure doesn't depend on rotation of fluid elements. It only depends on deformation of fluid elements. And so we'll build that in to the structure. What I'll be talking about here, we will use neural networks to determine the descriptors and the evolution equations. I'll talk a little bit toward the end about some initial steps that we're taking. So if you have approximate governing equations, for example, then you can use those as well. We're using neural networks because they're flexible and general. They're very, very useful black box function approximators. Okay, so then there's just a little flow chart here. We have the data. We're going to transform that data into a phase-aligned frame, reduce the dimension, learn the time evolution, and map back. Ultimately, I'll talk a little bit about what we're doing in terms of velocity fields. So this part is actually not so straightforward. I should sort of have this grayed out because you can't directly determine the stress from velocimetry. There are limitations, fundamental limitations to that. All right, so what I'll talk about is work that we've done with synthetic data. So we generated the flow with CFD, we just used OpenFOAM, and we generated the microstructural evolution with Brownian dynamics, which is very easy for dilute rigid rods, okay? So we're in the process now of basically transferring that framework that we set up for synthetic data and using it on real data. Okay, so just keep in mind, so whenever I say data from here on out, it's data in the sense of simulations, okay? All right, so let me just talk about symmetries for the moment. If you're paying attention, or if you're involved in scientific machine learning, you'll know that building symmetries that you know from the physics into the framework is a major aspect of scientific machine learning activities. There's all sorts of symmetries that show up in physical systems, everything from simple translation invariance to Hamiltonian structure, and so people are working to build those into their framework so that whatever you get out automatically satisfies those symmetries. So in our case, there are two that we care about. One is just that, if you have a rotated scattering pattern, but the material microstructure is otherwise unchanged, right, then you can factor out an angle variable. And so we just do that in a simple way. You can think of, so here again, this is just from our simulations of the rigid rods. So the scattering pattern is oriented this way, which means that the microstructure, the rods are oriented this way in this case. And so you can identify an angle and factor it out. All right, and so what we're going to do on all of our data is we're going to have a phase-aligned scattering pattern and an orientation angle, okay? The other symmetry, which is not kind of trivial, is the dynamic symmetry of material frame indifference. And that's that our microstructure should only depend on the local evolution of the microstructure, only depends on the strain rate, not the rotation, not the vorticity, right? So the vorticity, local rigid motion component of the velocity gradient, that's just rotating the microstructure. It's not actually stretching it. It's not actually changing the microstructure. The way we're doing that is by learning the evolution equation in a reference frame that's co-rotating with the vorticity tensor. So you can think of a matrix Q that's got orthogonal coordinates, and those orthogonal coordinates are evolving according to this kinematic equation. All right, omega transpose is just the omega is the vorticity tensor. And then in the rotating coordinate, the velocity gradient, the rotation gets factored out, and you're just left with a rate of strain. Okay, and so just if these movies work. So here's the result so this is simple shear in a lab frame, right, where the flow is steady. In the co-rotating frame, the local vorticity is this way. The scattering pattern is steady. So in this frame, it's rotating backward. And then we can learn a time-dependent orientation angle so that instead of the scattering pattern changing, only the orientation angle changes. All right, and that saves us a lot because one thing that means, well, first of all, it means that these symmetries are automatically built in. If you didn't automatically do that, you would have to separately learn this scattering pattern, and you'd have to augment your data with that scattering pattern, and then all rotations of it to have a proper data set. And that's that data augmentation step. That's one way to deal with things. It's approximate and it's expensive. So if we factor out the symmetries, we can save a lot of time and then guarantee that those symmetries are satisfied numerically exactly. Okay. All right, just a little bit of detail. All we've done here, this isn't, people have been interested in extracting orientation angles from scattering patterns. So nothing we've done here is particularly new. You can just pick a little radial region and look at the intensity as you go around and just plot that intensity, and you can see where that peaks. You can take the second Fourier mode here and find the phase angle for that second Fourier mode. All right, so that's how we find the phase angle. And then a reviewer asked us about this. So we just did an example of working in the co-rotating frame. So this is just the upper convected Maxwell model where S would be some kind of second moment tensor, stress tensor. So in a frame indifferent tensor transforms this way. So in a nutshell, if you go into the rotating frame, the evolution of this tensor now in the rotating frame with the superscript R only depends on the rate of strain and the stress. So the vorticity has vanished from this formulation. So instantaneously, you only depend on the local strain rate. Okay. All right. So that's the kind of the symmetry piece. Let me talk about the dimension reduction piece. So the scattering patterns are fairly big. So 100 by 100 pixels. For example, we would like to have a representation that's much more compact and ideally a representation that's minimal, that only contains the essential number of degrees of freedom to represent that are needed to represent the structure. And so we've done this in 2 steps. So we have a lot of data. So we have our data set is scattering patterns along a whole bunch of streamlines. Okay, so a certain number of scattering patterns per streamline times the number of streamlines that we look at, and then times the number of flow fields we look at, or different flow types. So there's a fair amount of data. We can take all of that data and we do an initial dimension reduction step just with principal components analysis. That's a linear dimension reduction step. And in this case, so if you're in fluid dynamics, which I live half my life in, that's proper orthogonal decomposition. So linear dimension reduction method, it's the best linear, least squares best linear representation of your data with a certain number of degrees of freedom. So we do that first down to say 50 degrees of freedom. And then we use a nonlinear dimension reduction method called an autoencoder to reduce it even further. We have a particular flavor of autoencoder, which was developed by Jan LeCun's group that we've kind of tweaked, that actually gives you an explicit estimate of the number of dimensions that you need. An autoencoder simply is a nonlinear mapping from a high dimension to a low, and another nonlinear mapping from low back to high. And you learn those 2 mappings as neural networks so that your output matches your input. That's what an autoencoder is, okay? And so what we're able to find for the data sets, for our synthetic data sets, is that, so the phase angle is 1 degree of freedom. So that's what's keeping track of the orientation of our scattering pattern. And then we need 5 other degrees of freedom. This is just the singular value decomposition of the of the data in the latent space, we have 5 substantial singular values, and then the rest are very small. So we throw all these away, and so we have a 6-dimensional representation of the dynamics of these rigid rods. Okay, which kind of makes sense if you just think about the second moment tensor for the rigid rod. So in 2D, it's symmetric, so that would be 4. We're at 6. We know that for rigid rods, you can't write a closed evolution equation just for the second moment tensor. You need moment closures, so there's other degrees of freedom. So we end up with 6 degrees of freedom, which seems pretty reasonable. So one question that often comes up here, and so I'll say a little bit about it now, is this is a description that's in some sense optimal. It's minimal, right? We have negligible error going from our 10,000 degrees of freedom down to 5 degrees of freedom plus a phase, and then back to our 10,000 degrees of freedom. All right, but it's not interpretable. We have this, so PCA you can argue is interpretable because it's the best, linear dimension reduction scheme in a least squares sense. So that means interpretable to you, then fine. And then we have this nonlinear piece and descriptors that individually don't have any particular physical meaning, right? So that, just to be clear on that. We could have said, well, we're going to do second moments, or just do a moment expansion of the scattering pattern. You can do that. We haven't done it. We're going to do it. That in general probably requires more degrees of freedom than this description. All right. So to my mind, there's a trade-off in general between minimality or optimality and interpretability. All right. So if wherever you come down on that side of the trade-off, that's going to determine what you want to do here in terms of this dimension reduction piece. I'm happy to talk about that further. Okay. And so now we have, for each of our scattering patterns, we have this minimal descriptor representation. And now what we're interested in doing is finding the time evolution of that representation. So this is already frame indifferent. And so what we've done here, again, so this is not interpretable. So what we're going to learn is an evolution equation for H. Sorry, I should have introduced that. H is standard nomenclature for latent variable description. So H is our set of descriptors. Alpha is our phase angle that also is undergoing an evolution equation. These depend on alpha. It turns out to be convenient to parameterize alpha with sine and cosine. And then this is just the transformed velocity gradient. Here we have the transformations for both the phase alignment and material frame indifference. Here you just have the material frame indifference piece because you're learning the phase alignment piece. And there's a framework that we've used in other contexts. A lot of people have used this now in various contexts now, called a neural ODE framework. And the basic idea is if you have data at discrete times, okay, I can pick a right-hand side. I can evolve. So I can evolve from my known initial condition, which is the data at time t, evolve forward to time t plus tau. All right, and then I can use that, and then I need the derivative of that time evolution operation with respect to your neural network parameters. You can do that in a couple of ways. You can do that with classic adjoint-based optimization methods. You can also do it now with modern programming languages. You can just do it by autodiff through your ODE solver. They have those two approaches have different advantages and disadvantages. They both work on the problems that we've looked at. And so that's what we do here. And I can talk about that in more details. Here, we've been completely agnostic to the structure of this. We just let the data determine it. If you know something about the structure, you can use the same framework, but only have your unknown parameters being, for example, you want to learn an interaction potential. but otherwise you have the governing equation. So you can do that as well. And then if you also have stress measurements, which you might from some kind of Rheos-Sachs measurement, then you can also learn the relationship between the microstructure and the stress. You can't get that directly from the experiments. You can't get that directly from velocimetry. Okay, so that's the framework. So let's see how that works. So as I said, our training data is we have lots of streamlines from lots of different flows. So we have training data. So here's a bunch of streamlines. And then what we've done here is here's our test streamline. So this is a streamline that's not in the training data set. You can see here, this is just the flow type versus Lagrangian time. You see that actually changes from positive to negative to positive. So this isn't, uniformly a shear flow or extensional flow. As you're moving along here, it becomes strain dominated and rotation dominated, depending on where you are. So here's the data. This is just the Brownian dynamics. Here's the model that came from our dimension reduction and time evolution pieces. Here we've just subtracted one from the other. You can see that the error, this is on a different scale than this. So the maximum error here is about 10%. Maximum relative error is about 10%. The ensemble average relative error is generally just a few percent. Okay, so we're able to capture quite well the evolution of the microstructure. We can do this along a large number of streamlines and again get small errors. This is just if you learn a function for the stress here, this is just sigma xx and sigma xy, then you can capture those very well also. Okay. One thing that we didn't do in the training was simple startup flows, startup of steady shear or planar extension. And so we've now we're showing the results. So this is the data, again, data in quotes. These are the steady state data, steady state model predictions for startup of steady shear at a variety of Peclet numbers. And we agree very well. Our data, so Peclet number, the local Peclet number is varying from point to point in these flows. We just estimate a Peclet number based on the strain rate at the stagnation point, right? But we can actually extrapolate a little bit. The dashed boundary there is outside the region of Peclet number where we have data. Works okay. This is startup of steady extension. This is the data. This is the model. Here, the model is failing out here. The white means that the intensity is negative, which you can't have a negative scattering intensity. So there's a limitation to our predictions out here. What we actually think is that you just need to use more PCA modes because there's a bit of Gibbs type phenomenon here because the scattering patterns are becoming very strongly localized. If you don't, basically in a linear representation, if you don't include enough modes, you get Gibbs phenomenon. So that's what we think is going on there. We can, just go back, and even though we haven't done a rheometry experiment, we can go back and extract the shear viscosity in this case at a variety of. Actually, I haven't shown the extensional flow data here, so that shouldn't be here. So this is the data. This is just from the Brownian dynamics simulations. This F here, that's just the stress function that you can learn from we know the stress for dilute rigid rods, so we can find that. So I guess the data is the true. The orange, this is the neural network approximation of the data. And then here's the results that come from time evolving, the startup of steady shear experiment. The except at very low Peclet number, where there are a couple problems. First of all, we don't have much data at very low Peclet number. And second of all, with the Brownian dynamics, at low Peclet number, you have high noise. And so that's I think, the source of the error there. We don't do too bad a job, despite the fact that this model has never seen simple shear. data. Okay, so we're doing okay. All right, let me just spend a few minutes talking about some things we're working on now. So right now, the only physics that we've built in is material frame indifference and the basic symmetry of the scattering patterns. In other contexts, we've developed a method where if you have a known governing equation, so some partial differential equation. So imagine the Smolkowski equation for the orientational distribution function for our rigid rods. Develop a low-dimensional representation of the data. You can do a nonlinear projection of the governing equations down onto your lower dimensional coordinates. So H here is the latent space. That method was developed a few years ago. That's called manifold Galerkin. It's not actually reduced order because you have to go back and forth between the low dimensional and high dimensional representations to do time evolution of this. But you take data for this and you can learn a neural network, essentially a neural network for the vector field. And then you can use that, actually what works best is using that as a Bayesian prior for a model that's also adapting to your data. All right. We haven't done this yet for this rheology problem. We've looked at it for some spatiotemporal chaos problems. And so this is just ensemble average relative error versus time scaled with the correlation time for this data. The two curves to look at are data. I didn't tell you what this acronym means. Data-driven manifold dynamics. We have a low-dimensional manifold where the data lives. So that's the purely data-driven approach. Here's the approach where you use the governing equations as a Bayesian prior, and you can actually reduce the ensemble average at 1 Lyapunov time by a factor of 2 by using the built-in physics that you have. Even if the physics is wrong, this is actually in the case where the parameters that we gave the first principles model were incorrect. You can fix that error in the first principles model with the data. All right, and the last thing I'll talk about is that, so we also have velocimetry data here. And so what can we learn from the velocimetry data? One thing we can learn is, so we know the momentum equation. Here's the momentum equation. We've neglected inertia here. So what we can do is ask the question, well, what's the optimal solution to the momentum equation what's the solution to the momentum equation that minimizes the error relative to the measured data? Okay. The unknown in that case, the handle that you have is the force density in the momentum equation, the divergence of the stress tensor. And so in principle, if you have velocimetry data, you can find both the velocity field that satisfies Stokes or Navier-Stokes and the corresponding force density. Turns out you can only find from velocimetry, you can only find the divergence-free part of the force density. If you don't have any pressure data, it's just like in Newtonian fluid mechanics. You can't learn the pressure from the velocity, right? It's even worse in complex fluids because it's the stress tensor rather than just a scalar pressure. But you can, at the very least, and we've done this just for a model problem, which is a cellular flow, so a sinusoidally forced flow, that there's stagnation points at each of these corners. So this approach, it's called data assimilation. This approach, we can find the velocity field. So that's useful because we're going to need a good velocity field for all of the work that we're going to do on finding the evolution equation, because we need the velocity gradient. So if you have a bad estimate of the velocity gradient, you're going to have a bad estimate of the microstructural evolution. So at the very least, we can get the velocity components. You can also get some information about the polymer stress in terms of the divergence-free part of the force density. Can we get the stress tensor from the force density in microstructure without assuming a particular constitutive equation? I don't know the answer to this. We think it might be possible, but that's I think an open question. If you assume a constitutive model, you can do it. It's not a hard problem. But if you want this agnostic to the constitutive equation, then there's a lot more work that needs to be done. All right, with that, I will wrap up just by talking about what directions we're going in. We want to move from synthetic to real data. We're doing that now. There are all sorts of various issues, practical issues in terms of interpolations, approximations, and noise. What we would really like to do is have a setup where if you have scattering data, birefringence data, Reo-Sachs data, you can just put that all in the framework and develop these microstructural evolution models. So that's something, we kind of have a framework set up for that, but that's work in progress. I kind of hinted at building known but approximate governing equations into the framework. We've done that in other contexts. We're in the process of doing that here. And I mentioned at the beginning, the four-roll mill geometry is not obviously the best geometry for looking at particular processing applications. Okay, and then it would be really interesting to be able to extract as much as we can about the actual stress field as well as the microstructure. So with that, I will wrap up, and I hopefully I've left a little time for questions.
Sure. Did you guys characterize or have any idea what the shape dispersity is for your CNCs? Because I know depending on how you prepare those, it can be very different, and I mean they're not rigid rocks.
So in our simulations, they're all the same length.
Well, sure. In reality,
no. I know that Matt has worked hard on that. I couldn't give you a precise answer to that question. Yeah. But I know, but he could. I'm sure that he could.
Thanks.
Sorry. But, yeah.
Can you say a few words on how?
Oh, sorry, we use the microphone for the questioners.
Can you say a few words on how one determines the stress?
So, so the stress is under the divergence operator. So we have part of the force density, the divergence-free part of the force density. The stress is under the divergence operator. The problem with that is that the divergence operator has a non-trivial null space. So you can't uniquely determine the stress from the force density. What we think it should be possible to do is if you also have microstructural data, then you should be able to determine a stress field that's consistent with the force density and consistent with the microstructural data, right? You have additional degrees of freedom that gets rid of that hopefully would get rid of the degeneracy that you have just from the divergence operator. That we think should work. But I'm not, that's where we're going with this. And even that, you can only get the stresslet. You can only get the deviatoric part of the stress. Unless you have pressure measurements, normal stress measurements somewhere, then there's a whole part of the stress that you don't have access to. So you're going to need Reo-Sachs data where you have normal first and second normal stress differences and microstructure, right, to get a full description of that.
There's a question of
So your the G's that you had in your dynamical models,
Yeah.
they're basically just neural networks.
They're neural networks.
Have you tried something like where you mentioned that if you know an example of like a microstructural evolution, so
Yeah.
you know that kind of like analytically, basically, have you tried using something like Cindy, where you can basically, use like an L1 minimization to find functional formulas just to check?
Yeah, so we've done more than Cindy. So the part that I went over very briefly is, so Cindy's quite limited really to low dimensional representations. You're choosing a dictionary and finding coefficients in front of the terms in that dictionary. We'd rather just let it be a neural network where we have much more flexibility. And so we've done that where basically you're learning the vector field from your approximate model as a neural network. You could use Cindy as well if you prefer. And then we use that representation as a prior for the data-driven model. Bayesian prior. So basically it's a penalty term on the loss to learn the data-driven evolution equation. Yep.
This will probably be the last question.
Very interesting. I wanted to ask, how do you know what's unknowable? So you mentioned that of course you can to get the pressure out. Is that something that you learn, or is that something that you have to put in by hand?
No, well, yeah, in terms of the stress, that's a great question. I mean, there's the mathematical problem of you don't get a unique stress tensor out of the force density. And so that's kind of the question we're at right now, is how much information about microstructure would we need to add to our force density measurements to extract, you know, as much as possible from the stress tensor. I wish I could give you an answer to that. Maybe, yeah, I won't make any forecasts.
Okay, thank you very much.